For like half a century now, physicists have been staring down a problem so fundamental it threatens to break everything we think we know about the universe. Today, we're going to dig into a wild new idea that might just solve it.
At its core, the whole thing is a paradox. It boils down to this impossible choice, right? A direct conflict between our two pillars of modern physics, general relativity and quantum mechanics. So for 50 years, physics has been totally gridlocked. On one hand, you've got quantum mechanics, which says information can never ever be destroyed. On the other, you've got general relativity, which says nothing, not even information, can escape a black hole. You can't have both. It felt like there was no way out.
But what if the problem isn't with the answers we've been finding, but with the question we've been asking? A new framework is suggesting that maybe, just maybe, we've been looking at black holes completely wrong from the very beginning.
Okay, so let's dive into this. To even begin to untangle these paradoxes, we have to kind of throw out our old definitions and start fresh.
So here's the absolute key. Stop thinking about a black hole as an object made of crushed up stuff. Instead, think of it as a state of maximal coherence, where information is packed together as perfectly and as stably as the laws of physics will allow.
And that famous event horizon, the point of no return? Well, in this new picture, it's not some physical wall you'd crash into. It's more of a limit to our perception. It's simply the point where the information inside gets so perfectly ordered that we, on the outside, can no longer read it. And this is where it gets really clever, how it explains Hawking radiation. They have this great name for it, the Gödel residue. It's a nod to the mathematician Kurt Gödel, who proved that no logical system can be perfectly complete. Well, the same idea applies here. Even this state of maximal coherence can't be 100% perfect. It has to leak a tiny, unavoidable bit of imperfection. And that leak, that's what we see as Hawking radiation.
All right, so now that we have these new definitions, let's go back and attack that first big paradox, the problem of lost information, and see how this new way of thinking just makes it dissolve.
The answer, it turns out, is beautifully simple. Information never disappears. It just gets filed away. It's integrated into the most perfect, most stable storage system imaginable. It's not gone. It's just inaccessible for a very, very long time.
So imagine you drop a book into a black hole. All the information in that book, every word, every atom, it gets seamlessly woven into the black hole's perfect order. Then over these unimaginable timescales, we're talking 10 to the power of 100 years, that information slowly, painstakingly leaks back out, scrambled up within the Hawking radiation. So boom, information is preserved, quantum mechanics is safe.
Okay, so that handles the information paradox. But what about that other terrifying idea, the firewall? The theory that an astronaut would be instantly incinerated at the event horizon? Well, according to this framework, nope, not going to happen. See, the whole firewall idea only works if you think of the event horizon as this sharp, violent edge in space-time. This new model says that basic assumption is just wrong. It's not a wall. It's a smooth, gentle slope, a continuous gradient where things just get more and more and more ordered.
So instead of a violent crash, an observer's information just merges. It becomes part of that perfect coherent state. You don't cross a boundary, you become part of the structure itself. And just like that, general relativity is also preserved. No drama, no fire. Now, if this is all true, it completely changes the role black holes play in the universe. They're not just cosmic vacuum cleaners. They have a purpose. So, what is it?
The idea is actually kind of beautiful, almost poetic. Think of a galaxy as having two modes. You have the stars, the planets, life. That's where the galaxy thinks. It's dynamic, messy, always changing and processing new information. But the black holes? That's where the galaxy remembers. That supermassive black hole at the center of the Milky Way isn't just a gravitational anchor. It's our galaxy's archive. It's the maximally compressed, permanent record of everything that has ever happened here. It's a cosmic hard drive.
And here's the best part. This isn't just some neat philosophical idea. This is real science. It makes specific, testable predictions that we can actually go out and look for to see if it's right or wrong.
So what's on the checklist? The theory predicts that Hawking radiation isn't just random static. It should have hidden patterns. It says that the gravitational waves from merging black holes will carry echoes of their pasts. It even suggests a deep connection between the central black hole and the story of the galaxy around it.
These are all things we can actually test.
One of these predictions, though, is incredibly precise. It gives us a hard number to look for, a clear signal that our gravitational wave observatories might be able to detect right now.
Here it is. The theory says if we see two pairs of black holes merge, and they have the exact same mass and spin but different histories, their ring down, that's the signal as they settle, will have frequencies that differ by about 0.1%. Their unique informational history should leave a tiny but measurable fingerprint on space-time itself.
So you see, it all comes back to this one crucial shift in perspective. By redefining what a black hole fundamentally is, this framework makes 50 years of paradoxes just melt away. It's not a destroyer, it's a preserver.
And that leaves us with one final, awe-inspiring thought. If the supermassive black hole at the center of our own galaxy is a hard drive containing the entire story of the Milky Way, what's written on it? And what happens if, one day, we learn how to read it?